In this lesson, we're going to talk about an integration technique called substitution. And so in previous sections, we've been starting to develop our skills and getting comfortable with the fundamental theorem of calculus without having to deal with geometric formulas or even the messy definition with the Riemann sums. So what this technique does is it helps us take a function that we're trying to integrate that's very complicated, and we break it down and make substitutions to make it a very simple function. So here highlighted in yellow, we have a problem-solving strategy that we can look at step by step. The first step says, look carefully at the integrand and select an expression, g of x, within the integrand to make your substitution. So when we're looking for that expression to make a substitution, we want to really think about inner functions. What is our inner function? A lot of times that is what's going to help us find what we need to set equal to u. So thinking about the chain rule and working backwards will really help us with step one. Now, sometimes you make a substitution and it doesn't work, and then you have to go try a second substitution to see if that works. It happens. If you need to do it, just do it and don't worry about it. So in step two, you're going to substitute u in for that expression that you chose, and then you're going to rewrite du in terms of dx. Because once you write the integral in terms of u, your variable of integration is no longer going to be x or t or whatever it is. You need to write that in terms of u. Then the third step is we're going to then take the integral with respect to u. And part 4, if it's a definite integral, then we have to evaluate the integral in terms of u. If it's not a definite integral, then we don't have to worry about that step. Once we finish integrating, then the last step is to then go back and substitute in so we have everything back in terms of x. So we're going to start off with a nice simple example here. So if you notice here, this 3x squared plus 4 to me looks like an inner function, where the outer function would be something raised to the 4th. So I'm going to start off by letting u be equal to 3x squared plus 4. And like I said, sometimes your first substitution doesn't work and you have to try another one, which is totally fine. So once you find your substitution, you're going to find du with respect to x, because our variable here is x. When I do that, I'm going to get 6x. And then I'm going to multiply both sides by dx, so I get that du is equal to 6x dx. So now I'm going to rewrite the integral 6x times 3x squared plus 4 to the 4th dx, and I'm going to make my substitutions. Notice that du can replace 6x and dx. So I'm going to get rid of 6x and dx, and I'm going to replace that with du. Then I'm going to replace 3x squared plus 4 with u. So now I know that this integral is set up now for substitution because now I have everything in terms of u. If you still have x's in that integrand, then you did something wrong, or you need to go back and try a different substitution. But when you substitute, you should change it all into one variable. Once you do that, then we can integrate. So I'm going to find the antiderivative of u to the 4th du. This is much easier to find the antiderivative of compared to 6x times 3x squared plus 4, all raised to the 4th. If I find the antiderivative of u to the 4th, I'm just using the power rule. So I have u to the 5th divided by 5, and then I write in my plus c. Now, because this is not a definite integral and we're not evaluating it over an interval, I want to make sure that I still put that plus c in there because that does exist. But when we evaluate it with a definite integral, remember we subtract and we end up getting rid of those constants. So for indefinite integrals, we want to make sure that we put that plus c in there. So here's our antiderivative, but this is in terms of u. The question asked us in terms of x. So now we have to go back in and resubstitute everything that we have for u back in terms of x. So u, we said, was 3x squared plus 4. So in parentheses, I'm going to substitute u for 3x squared plus 4, and that's all raised to the 5th. And this is divided by 5 plus our constant. Now, if you want to double check to make sure this works, this is our capital F of x. If I take the derivative of this, I should get 6x times 3x squared plus 4 all raised to the 4th. If we work backwards, we can check it that way. In this next example, we're going to use substitution again, but we're going to have to make some more manipulations for it to work. If you notice, we have the indefinite integral of z times the square root of z squared minus 5 dz. The first thing I like to do, just because I prefer using powers instead of roots, is I'm going to rewrite this as z times z squared minus 5 to the power of 1/2. Then I'm going to try a substitution. To me, this looks like it would be the inner function, so that's what I'm going to set equal to u. I'm going to say u is equal to z squared minus 5. And so I'm going to take the derivative of u with respect to z. That will be 2z, and the minus 5 drops off because when I take the derivative of a constant, that's 0. Now, notice up here, I have to replace z and dz. So what I'm going to do is I'm going to multiply both sides by dz, and I get 2z dz. But what I need to replace is z dz. So I'm going to isolate this and divide both sides by 2. So I have 1/2 du is equal to z dz. So now I know I can replace z dz with 1/2 du. And now inside here, I'm going to replace z squared minus 5 with u and raise it to the 1/2. Now I have everything in terms of u, and I can integrate and find the antiderivative. So the trick is that you want to manipulate your expression to make sure that you replace everything with u's. All right, now when I take the antiderivative of 1/2 u to the 1/2, I'm going to add 1 to the exponent, so that gives me 3/2. And then I have to divide by 3/2. And then I have my plus c. When I clean this up and I take 1/2 divided by 3/2, I do a flip and multiply, and I'm going to get 1/3 u to the 3/2 plus my constant c. Now my last step, since the question was asking us to find this in terms of z, is to go ahead and resubstitute u. So now I have everything back in terms of z. So I have 1/3. I'm going to replace u with what I originally substituted it for, which is z squared minus 5. And that's all raised to the 3/2. And I have my constant. In this next example, we're going to try substitution with trig functions. So I have the integral sine t over cosine cubed t dt. I personally, especially when we're doing substitutions, like to rewrite any trig function that's being raised to a power like this. Instead of having cosine cubed t, I'm going to write it like this, cosine t cubed. So then I can recognize a lot easier what I need to use as my inner function. So I'm going to let my inner function be cosine t. So I'm going to take the derivative of u with respect to t, and I take the derivative of cosine, I get negative sine, and I'm going to multiply both sides by dt. Now notice what we have to replace. I have something to replace cosine t with, that's u, but I still have to replace dt sine t. So I need to isolate sine t and dt, so I'm going to divide both sides by -1, and I get negative du is equal to sine t dt. So now I can replace that sine t dt with negative du. So now I have 1 over u cubed, and I can replace sine dt with du and a -1. And if you want, remember with your properties of integrals, you can pull out constants. So I can actually pull the -1 in front if I'd like and write it like this. So now I need to integrate 1 over u du, and it might be easier to write this as u to the -3rd, so we can use the power rule. So when I find the antiderivative of u to the -3rd, I'm going to write this as u to the -2 because I have to add 1 to -3 and then divide by -2, and then I have my plus c. The two negatives make that a positive u to the -2 over 2 plus my constant. I don't have to write my constant as a minus c because that constant is arbitrary, but you can if you want. Now I can go ahead and resubstitute u for cosine t. So I have cosine t raised to the -2 over 2 plus c. And then if I want to write it without negative exponents, I can write my final answer as 1 over 2 times cosine t squared plus my constant. This will be our last example with indefinite integrals and use substitution. And then we're going to go on and practice a few examples with definite integrals where we have to actually evaluate as well. So we have the integral x over the square root of x minus 1 dx. I'm going to substitute and let u be equal to x minus 1 because I recognize that that's probably going to be our inner function. I'm also going to go ahead and rewrite this as x minus 1 to the 1/2 because I prefer using powers rather than roots. Now when I take the derivative of u, I'm going to do it with respect to x. Du dx is equal to, and now I have the derivative of x, which is 1, and then the derivative of -1 is just 0. When I multiply both sides by dx, I get that du is equal to 1 dx. So when I go to make my substitution, downstairs, I'm going to have u to the 1/2. I can do a direct substitution for dx and write it as du because we found that du was dx. Now, the question is, how do we get rid of that x on top and write it in terms of u? Well, we have this formula right here. U is equal to x minus 1. So if I write x in terms of u, I would add 1 to both sides. So now I can replace x with u plus 1. So now I have my integral all in terms of u. Now, before I integrate, I'm going to simplify this. I'm going to break it up into fractions and simplify my exponents. So I have u over u to the 1/2 plus 1 over u to the 1/2 du. U over u to the 1/2 is going to give me u to the 1/2 because I subtract my exponents, 1 minus 1/2. And then I can write 1 over u to the 1/2 as u to the negative 1/2. Now I can find my antiderivative. If I find the antiderivative of u to the 1/2, I have to add 1 to the exponent and divide by that exponent. So I have u to the 3/2, and I'm going to divide by 3/2, which means I'm going to multiply by 2/3. Plus, I'm going to add 1 to the negative 1/2 power, which gives me u to the 1/2. And now I have to divide by 1/2, which is the same thing as multiplying by 2. And then I'm going to add my constant. So now I have to go back and substitute everything back in. So I had that u was x minus 1. And I have to substitute u in here as well. And then my plus c. So this is my final answer. Unless, of course, you want to combine those fractions and try to simplify further, but leaving it like this is fine with me. Now we're going to go through a few examples of using substitution when we have upper and lower limits and we're actually evaluating a definite integral. The process is the same up until we have to deal with evaluating with the limits. So we're going to find our inner function that we can use for substitution. So I'm going to let u be equal to 1 plus 2x to the third. Now I'm going to take the derivative of u with respect to x. The derivative of 1 is 0. When I take the derivative of 2x to the third, that gives me 6x squared. I'm going to multiply both sides by dx. I have 6x squared dx. So if I replace that 1 plus 2x to the third, we'll have u to the 5th, but we still have to replace x squared dx. So I need to isolate the x squared dx to see what I need to substitute that with. So I'm going to divide both sides by 6. And I get 1/6 du is equal to x squared dx. So now I see what I can substitute x squared dx with. I'm not going to do anything with the limits yet. I'm just going to show you how we're rewriting the integral without the limits. So I'm replacing x squared dx with 1/6 du. And then I replaced inside the parentheses 1 plus 2x to the third with u, and now I have u to the 5th. So now I have this written in terms of u. However, now we have to take into consider our upper and lower limits. 0 and 1 were written to be plugged into x, so those are in terms of x. So we need to find out what those limits are in terms of u. So we're going to figure out if x is 0, what's u? So if I plug in up here, I'm using this right here, u is equal to 1 plus 2x to the third. So I'm going to find, if I plug in 0 for x to the third, I'm going to get that u is 1. Now I'm going to find if x is 1, what's u? So I need to plug in 1 for x. I cube it, I get 1. Then I have 2 times 1 is 2 plus 1 is 3. So when x is 1, u is 3. So now I need to rewrite my limits. Other than that, we're doing everything the same as what we were doing before. We just have to add in adjusting our upper and lower limits as well. So now I'm going to find my antiderivative. I have 1/6. Now when I take the antiderivative of u to the 5th, I have to add 1 to 5 and divide by that same exponent. And since I'm doing a definite integral, I'm not going to worry about adding in my plus constant because I know it's going to be canceled out when I subtract and I evaluate. So I'm going to evaluate this from 1 to 3. So I can rewrite this as u to the 6th over 36, evaluated from 1 to 3. So I'm going to plug in 3. I'm going to get 3 to the 6th over 36. And I'm going to subtract 1 to the 6th over 36. When I do that, I'm going to get 182 over 9. So that's going to be my final answer. Notice that because we're actually getting a value and we're not doing an indefinite integral where I end up with some function plus a constant, I don't have to worry about going back and resubstituting for u. I'm just going to get that value 182 over 9. Next example, we are going to practice evaluating definite integrals again using substitution. So I'm going to make a guess that my inner function is going to be 4x squared plus 3. Now don't forget, if you pick the wrong u and it doesn't work, just simply go back and try a different u. That's all there is to it. So I'm going to take the derivative of u with respect to x, and I'm going to have 2 times 4, which is 8, and then I decrease the exponent by 1. The derivative of 3 is just 0. So now I'm going to multiply both sides by dx. So when I rewrite 0 to 1, x e to the 4x squared plus 3 dx, I figured out to replace this with u, but I still need to figure out how to substitute x dx. So I need to isolate x dx. So I'm going to divide both sides by 8 so I can identify what to substitute for x dx. So I have 1/8 du is equal to x dx. So I'm going to replace the x dx with 1/8 du, and then I'm going to rewrite this as e to the power of u. Now I have to just readjust my limits. So when x is 0, I need to figure out what u is. And when x is 1, I need to figure out what u is. So I'm going to use my equation up here, u is equal to 4x squared plus 3, to figure out what that is. So when x is 0, u is going to be 3. When x is 1, u is going to be 7. Then I'm going to rewrite my limits to go from 3 to 7. So now I just need to find the antiderivative. So the antiderivative of e to the u is e to the u. That makes it easy. And I want to evaluate this from 3 to 7. So when I plug in 7, I'm going to get 1/8 e to the 7th, and then I subtract. Now I evaluated at 3, and I got 1/8 e to the 3rd. Now if you want, you can approximate that in decimal form and put that in on your calculator. If you do that, you're going to get 134.57. Okay, last example, we are going to use substitution to evaluate the integral from 0 to pi over 2 of cosine squared theta. So my initial reaction when I look at this, I want to rewrite this as 0 to pi over 2 of cosine theta and rewrite it so that this is squared d theta. And then I notice, and the reason why I did that is I noticed that I have this inner function in here. So I'm going to let u be cosine theta. So when I take the derivative of u with respect to theta, I get negative sine theta. And then when I multiply both sides by d theta, I get this. So I have already figured out how to substitute cosine theta. So this would be my u, but I need to figure out what to substitute for d theta. Now, if I solve this for d theta, I'm going to get 1 over negative sine theta times du is equal to d theta. And if you notice in this integral, I don't have any sine thetas. And I can't replace d theta and have du and thetas. I can't mix u's and thetas. I have to have everything in terms of u. So this actually is not going to work. So this is one of those times where I tried a substitution, it didn't work, so I have to try something else. So I'm going to go ahead and erase this to make myself some more room. Now, another thing that comes to my mind that we could try is if I remember my trig identities, I remember that we had a trig identity that cosine squared theta is equal to 1 plus cosine 2 theta all over 2. So I'm going to try this substitution. So I'm going to replace cosine squared theta with this in my integral. So I have from 0 to pi over 2, 1 plus cosine 2 theta all over 2 d theta. So I just replaced this with this using our trig identity. Now I'm going to try to break this up and simplify this a bit. I'm going to rewrite this as 0 to pi over 2. I'm going to break up my fractions and write it as 1/2 plus cosine 2 theta over 2 d theta. Now I can split it up using my properties of integrals. I can say that this is equal to 0 to pi over 2 of 1/2 d theta plus 0 to pi over 2 of cosine 2 theta over 2 d theta. Now this one here is easy to find the antiderivative for. The second one here, I'm going to have to do a substitution. I'm going to carry this down here because I'm starting to run out of room. So I have from 0 to pi over 2, 1/2 d theta plus, now I'm going to set up a substitution and see if this will work. My inner function is going to be 2 theta, so I'm going to let u be 2 theta. So when I take the derivative of u with respect to theta, I'm going to get 2. And then when I multiply both sides by d theta, I get du is equal to 2 d theta. Now I need to replace d theta. So I'm going to divide both sides by 2. And I have du 1/2 is equal to d theta. So now I have everything I need for this substitution. So I'm going to rewrite this integral down here. I'm going to rewrite this as cosine u over 2, and I'm going to replace d theta with 1/2 du. Now I have to find my new limits. When theta is 0, so I'm going to plug that in here because this was our substitution. Our lower limit is 0, so when theta is 0, u is going to be 0. I'm going to replace that here. Now, when I plug in pi over 2 for my theta, and I take 2 times pi over 2, I'm going to get pi. So my corresponding value of u is pi when theta is pi over 2. So those are my new limits. So now I just have to integrate since I have everything set up. when I integrate 1/2 d theta, I'm going to get 1/2 theta from 0 to pi over 2. Now those limits I didn't need to change because I didn't do a substitution. So I can leave those as 0 and pi over 2. Now if I multiply those 2's that are in the denominator, I have 1/4. And when I take the antiderivative of cosine, I'm going to get sine u. And I'm going to evaluate this from 0 to pi. So now when I evaluate, I'm going to do this one first. I'll color code it so you guys can follow what I'm doing. I'm going to figure this out first. So when I plug in pi over 2 into theta, that's going to give me pi over 4. And I'm going to subtract what I get when I plug in 0 into theta, which is 0. So that's the first part here that I highlighted in orange. Now the next part, I'll highlight that in purple. I'm going to add that to 1/4 times, and then in here, I'm going to plug in pi. The sign of pi is 0. And I'm going to subtract what I get when I plug in 0 for sine. So the sign of 0 is also 0. So when I finish this up, I get pi over 4 minus 0, which is pi over 4, plus 1/4 times 0, which is 0. So my final answer is going to be pi over 4.